Good evening, good evening, good evening. So, how are you all, guys? I hope you would be fine and you are good. So, today we are going to start with our new chapter, that is work power energy. So, before beginning the new chapter, let me tell you a few things. You might be thinking that why we were not having our previous class, that was on our previous Sunday. Why didn't have a class? So the reason is quite simple. The day before Sunday or Saturday, we had our Independence Day. Okay, so belated Independence Day to all of you who are watching this lecture, and my salute to all the soldiers, those who have sacrificed their life, and freedom fighters, those who are working, and they all are really, we are proud for them, for their contribution to the country, how they sacrificed their life to protect the youth of the nation, for the people. How they did is amazing, and we need to remember those things. So, and also one more reason is that we have last the 2 weeks before we have finished our circular motion chapter. So I left the class, or I didn't, I skipped that day, because the circular motion chapter is a small chapter. Okay, it has not much weightage in the JEE mains, but JEE Advanced, I'm sorry, in JEE Advanced, but still it builds a basic concepts. Okay, basic concepts like angular displacement, angular acceleration. These all concepts will be used in our further chapters. Like, it will be used in our work power energy, it will be used in center of mass, it will be used in rotation, and also we can say that it will be used in SHM, oscillation chapter. Okay, so though the use of it is very less, but it is still important, because these chapters are having more and more number of weightage in JEE Advanced and JEE Mains. So let's start our today's chapter. So you may be familiar with the words work, power, energy, right? In our junior classes, like class 9, 10th, we are taught what is work, what is power. We learn a basic formula, we learn the formula for power, we learn what is energy, kinetic energy, potential energy, what do we mean by total energy. Okay, in some schools or some books there are taught, okay, we are taught the work energy theorem. Okay, some books we are taught mechanical energy conservation. Okay, momentum conservation we are taught. Yes, so these all things are we are going to deal in this chapter. So this is the chapter where we observe mechanics in a another way. Okay, in a different state, in something which is very different. Like, we know that whenever we do any work, we there is a energy which is involved while doing the work. In biology, in junior classes, we have learned that for doing any work we need energy, and that energy comes from food. We have learned, right, that we need energy to perform any action, perform any work. So similar to that, we can say that any work which we do in our daily life is can be related, or is involved with some energies and all this concept. So the first chapter of physics in class 11 is the unit and dimension, where we learn different units, what are dimensions, and the other things. And it is a beautiful chapter, very beautiful chapter it is. And we learn different units, how can we change units, how can we create our own, how can write our own formula. Okay, what are the dimensions, what do we mean by it, and it is obviously a beautiful chapter. If we see, we learn different principle of homogeneity. Okay, we learn how to find dimension of fixed quantity. Okay, these all things are really very important. Okay, and it is used also in physics in our second chapter, vectors. That is not a chapter of physics, that is chapter of mathematics actually, which we learn at the end of our class 12 mathematics. So there we learn about it, but it is really a very crucial topic. Okay, so we must not take it lightly, we must study. If we have not studied, if we directly come to this platform and started from circular motion, I will not recommend to do so, because you are not going to understand anything from it. Okay, so we need to study vectors, we need to study about components. So what are vectors actually? Okay, we learn that if an object, suppose if an object which is pulled from two different directions, or if we kick a football, two footballers, if this is the football, two footballers from two different directions are kicking it at the same time. So they have applied the force on the football from different direction, making different angles from the horizontal or from the vertical. So where would the ball go? This is a big question, right? So these all things how to solve. Okay, why, for any, what is vector quantity, what is scalar quantity, we are taught, which is at very basic level. How, why the vectors change if there are different angles. So we are taught many different things with this. Okay, we have learned different concepts. What are components? They are basically application of trigonometry. We just apply trigonometry to it, right? So we learn different things. We also learn more, what I can say, some theorems like Lami's theorem. Okay, we learn direction cosine. What is direction cosine? We are all going to repeat in class 12, but we have learned all these things, right? Then our next chapter, kinematics. Kinematics is divided into two types. One is motion in a straight line. We observe that how a body, how an object moves in a straight line. What is displacement? What is velocity? What is acceleration? What is distance? What is speed? We learn different physical quantities. We learn new physical quantities. We learn how to find them. We learn how to find acceleration. In our next chapter, that is motion in a plane, what we learn is that when an object is thrown vertically in making some angle with the horizontal, how it works, what is the acceleration in that case, what is the acceleration in the y direction, what is the acceleration in x direction, we all deal with this. I hope it is clear. We all, in this chapter, we all deal with this. What is the, so can you see, like, let me show you. In motion in a plane, what we learn is this, that if an object is thrown with a velocity u, then it, which makes an angle theta with the horizontal, then the path traveled by it is somewhat like this. Now this object is traveling in a xy plane. Okay, in a xy plane. We define this by writing like this. We represent it like this. So we can find the acceleration in the x direction, we can find the acceleration in the y direction, we can find the velocity. Now this is u, so there will be two components of u. So we deal with these things when we deal with the object, displacement, velocity, range, and some new terms we see, and we deal with them when the object is, or the body is traveling or moving in a plane, right? So in this chapter we focus this thing. Now our third chapter, which is the most crucial chapter for physics, that is Newton's laws of motion, where we study the 3 laws given by our famous scientist, famous physicist, Sir Isaac Newton. We study what is the reason for force. What is the reason for force? Why the force is applied? So that is acceleration, obviously. What is momentum? We now dive deeper into those quantities like displacement, velocity, and obviously we see some applications of Newton's laws of motion like pulley, tension, and then inclined plane, okay, uh, wedge constraint, and different applications we can find out. So that is a very important chapter. We learn how to make FBD, we learn how to find net force, we learn what is the reason of acceleration, and there are many things that we deal in that chapter. After that, what we learn a chapter, very small chapter but very useful. In some books, there is no chapter like that. We study that in Newton's law of motion only. So that is friction. Friction are of 2 types, static friction, kinetic friction. Now, in Newton's laws of motion, what we used to do, we used to study the things, we used to apply those things where friction was not present in maximum cases, right? Where friction was not present in maximum cases. So how would that we learn the basic concepts, and in the friction chapter we learn that if those things in our daily lives if they are the cases, then what should be the real approach? That chapter teaches us, because in our daily life friction is applied, okay? There is no such surface which is 100% completely smooth. So this is what we learned in our friction chapter, okay? We learned that it is a self-adjustable force, it is a necessary evil, and we gave many terms to it, many names according to the nature of it, the friction force, okay? Next chapter was circular motion, which we have covered here, okay? It is nothing but just the continuation of Newton's laws of motion. We defined some new physical quantities like angular displacement, angular acceleration, angular velocity, okay? And we just studied those same things, and just only in a circular path or circular track. Likewise, in the kinematics and motion in a plane, we studied the object were moving in a straight line and in a parabolic path, or it was thrown on a plane. We studied those things, but in this circular motion chapter we studied circular motion, okay, where the object was in, or we learned the cases where the object was, we found the same thing, we found the different physical quantities to show that how a particle moves in a circular track. So basically this is the continuation of mechanics only. Now the chapter which we are now going to begin is work power energy. So our work power energy is nothing but, as the name itself we derive, that we are going to in this chapter we are going to discuss about work, then what is power, okay? We are going to deal with different energies like kinetic energy, potential energy. We are going to relate these all 3 terms with each other. We are going to learn what are these things and how we can relate in our mechanics. So this is how we are going to extend our mechanics, and we are going to begin with our today's chapter. So I want to start today's chapter with a normal example, that if a block of mass is kept here and it has some acceleration in the positive x-axis direction, okay, in the I cap direction. So the object moves and it comes to rest at this. So this was the initial position, and this is our final position. Okay, so now what we can say, if there is acceleration and there is a mass, so there must be a force. And whenever we are doing, if there is force, we can say that there is some work which we are doing. Okay, when we are doing anything, so what was our basic definition? First we try to recall that whenever we move something, okay, like I'm giving a simple example which we studied. If I try to push the wall, I'm applying force, but the wall is not moving forward, so this is not an example of work. But if I'm pushing a table, and the table is moving a certain displacement along the component of force, then we say that work is done. So in this case, if the acceleration in this direction, so there must be a force which is acting upon this direction. So if there is a force and there is a certain displacement which we can say as x, so when we are having both force and displacement, we can say that there is a work done. So I hope this basic concept which we have studied in our class 9 and 10th is clear to us, right? So this is the basic definition for work. Now, when we are in our senior classes, we learn, in our junior classes, we learn that work done is equal to force into displacement. Okay, it is force into displacement. But let me tell you, this is not the complete definition. Okay, this is not the complete definition. But instead of this, the complete definition is that work done, value of work done is the dot product of force and displacement, force vector and displacement vector. So the work done is the dot product of two vectors. One is force and one is displacement. Okay, now in this chapter it may happen as we have seen in the Newton law of motion, that when an object is doing some motion, then there are various forces that is acting, like gravitational force, okay, the force that mg, weight is acting downwards, some normal force may act, tension force may act, there may act spring force. So there are different forces which is acting, okay, different forces. But what is this force? There may have confusion arise that what is this force? There are different forces acting. In this case also we can say that mg is acting in this direction, normal is acting here. Okay, then there is external force which is acting because there is acceleration in this direction. So there are three different forces which are acting. So what we have decided, that we are going to define work done for different forces differently. Okay, like let me show you that mg force which is going to act downwards, the mg force which is acting downwards, okay, it is having its own displacement. A force is acting downwards, but the object here is equilibrium in this direction. Okay, it is equilibrium in this direction. It is staying at this place only. Yes, it is moving in the x-axis, in the vertical, in the horizontal direction it is moving, but in the vertical direction it is in rest, right? So force is applied, but displacement, if it is in rest, what we can say, that displacement is 0. So for in this case, mg work done is 0. Similarly, normal is acting upward and the displacement is 0, so normal work done is also 0. But in this case, the force is acting in this direction and it is moving a displacement x, so this force is definitely going to have some work done, right? So we define work done differently for different forces. Therefore, what we can conclude that work done by this F is equal to F dot D, or dot product of F and T. Okay, so this is the basic concept. So whenever we are told to find the work done for tension, we are going to find the work done for normal, pseudo force and many other forces which we have studied previously in Newton's law of motion. So we have to only focus on the particular force. On that particular force we are only going to focus, because for different forces displacement is different, and as both forces and displacements are different, the work done is different for different forces, right? Are you able to understand? Okay, so I hope you are able to understand. Now so that you can write, let me write. So this is the force that work done whose work done we want to find. So this is that force whose work done we want to find. Okay, so in this case we want to find the work done for this force. So this is that force whose work done we are going to find. And similarly, this is displacement that causes because of that force. Okay, that is caused due to application that specific force whose work done we want to find. In simple word, I just want to say that suppose this is the force which is applied and the displacement which is caused because the effect of this force, so that should be our displacement. We are not going to take the displacement of mg, we are not going to take the displacement of normal, neither we are going to take the displacement of friction in this case. Okay, in this system we are going to take the displacement of that force only whose work done we need to find, whose work done we are going to find, whose work done we are asked in the question. So these are the important points which we shall remember. Okay, these are the silly mistakes which are made by different people, different students, and this is the basic concepts, right? This is the basic concept. So now let me erase this. Now, so work done is equal to F D cos theta. Okay, so work done is equal to F d cos theta, right? I hope you are okay with this definition. What is work done equal to? Work done is equal to F d cos theta. So this is the basic definition. This is the basic definition which we need to remember. Okay. So suppose an object of mass m has a force in this direction, which is making an angle theta with its horizontal, and this force has a displacement x here, okay, and it finally comes to this position. So now many people will say that why this f cos theta? Why f cos theta? So let me tell you that this force is going to result into two components, right? So what are those components? The first component is f cos theta, and the second component which is acting above is our f sin theta, right? F sin theta. Now a same force, one force is divided into two kind of force, right? Two types of force, or two components it is broken into. Now the displacement in this system is caused due to this force, okay, is caused due to this force, because the displacement is in the x axis. So therefore we can say that displacement is caused by this force. Now work done is equal to magnitude of force, that is f cos theta, into the displacement, that is x. So we can finally say that the total work done is fx cos theta. So this is the basic definition that we need to keep it in our mind. Now why that maybe a question arises that kinematics is so good, it is so easy to understand, we are solving questions, we are using the three equations which was given by Newton, we are using those equations, but why we are introduced to this chapter, we may feel this kind of things, right? So let me tell you that a basic concept and the most important concept, because this is the only concept, okay, this is the concept from this the JEE Advanced paper is asked, okay. That concept is, can you see that there is, suppose a work done in this system, there is a work done because there is a force and there is a displacement, suppose x, okay. So there is a work done, and whenever there is a work done, there must be some energy. In our junior classes we learn that the energy which is caused due to motion is kinetic energy, okay. Simply I can also explain it in a manner that, let me show you. Suppose this is the ground and a block of mass is kept here. There is a block which is kept here. Now I am lifting it above. I am taking it and I am lifting it. So it goes here and it finally reaches this place. So when I am doing this, I am applying a force which is against the gravity, okay. So these all things we are going to start study later, but still, which is against the gravity, so I am applying some force. So the net force caused by this and the gravity or the force which is applied, okay, and there must be a certain displacement, so there is a work done, and whenever there is work done there is energy. Okay, so in this case what happens, that object is kept here. When we are taking it upward, when we are taking it upward, our energy is stored in the body, that is the potential energy, right? And like this, when you are taking, so energy is stored in the body, that we call potential energy, and when we release it, see, it falls. So that potential energy is getting converted into kinetic energy, and that kinetic energy comes when the object is in motion. Okay, the object is in motion. We can also take a specific example, that is a rubber band. We have played with rubber band. We also use in our childhood, in our when we are very small, what we used to do, that we took those rubber bands, we took a piece of paper, we folded it, and we used to make it like a slingshot, right? And we used to play with those things. So when we are pulling it, when we attach the paper, and when we pull it, or when we attach the suppose some material we took, and when we pull it, so energy is stored, and when we release it, it goes forward, it moves forward automatically. We are putting some work, we are using some work to, okay, we are doing some work to store this energy, and because of that storage is in energy, when we are releasing it, it moves. So while moving, it releases kinetic energy. So the same potential energy which is stored is released by the kinetic energy. Okay, so just the same thing, or we can relate it like this. So similarly, what we can say, that whenever a force is applied and a displacement is there, there is a kinetic energy which is working because the object is in motion. So what do we say, that work done by all force is equal to change in kinetic energy. What does this mean? That work done by all the forces is equal to change in kinetic energy. That means kinetic energy final minus kinetic energy initial. So this theorem, which states that work done by all the forces in a system, like in this case, this force is acting, there may be friction force which is acting. If the surface is not smooth, mg must be acting. Normal is also acting because it is in contact with this surface which I can see here. So work done of mg plus work done of normal plus work done of friction plus work done of this external force is equal to final kinetic energy minus the initial kinetic energy. So this is the work energy theorem which states this. Okay, so for now I just want to introduce this theorem, and so that we can understand why this chapter is important to read, why we want to learn this chapter, what is so special that we have learned how to find the velocity, okay, and many other things. But why we are studying this chapter then? Okay, so we will just decode its importance in our subsequent classes, and when we'll study, while studying we'll decode it. But to understand its importance, let's take one more example. That is, if a block mass 2 kg is at rest and a force is applied, force of 20 Newton is applied on this block. The block moves a displacement x, okay, which is equal to 4 meter. Okay, 4 meter. Let's consider it is at rest, it is moving 4 meter, and so it must have an acceleration in this direction. And let me say that there is a final velocity. Okay, obviously there will be a final velocity. So I want to know what is this final velocity, right? So if we want to find the acceleration, we know that force is equal to mass into acceleration. So from this formula, acceleration must be equal to force by mass. So what is acceleration? Acceleration is force divided by mass 2 kg, that is 10 meter per second square. So this is the value of acceleration. Now we have acceleration. The object was initially at rest, so the initial velocity is 0. It is having sorry for this interruption. It is having some final velocity which we want to find, and the displacement is 4 meter. Okay, so these all are the things which we are given, and we want to find our final velocity. So we can easily find using the equation of motion which we were taught in the kinematics chapter. So if I use the third equation of motion, first let me write kinematics. Okay, so using third equation of motion, 2as is equal to v square minus u square. Okay, so 2 into 10 into 4 is equal to v square minus u square. U square is 0, so I am erasing it. So v square is equal to root over of 10 to 2 into 4. V is equal to this. So what is the velocity? Velocity is 20 into 4, that is root over of 80. So this is our final velocity which we are getting from kinematics. So we are getting from kinematics. Why we are studying this work energy theorem? Because there are certain problems which we can solve from kinematics, but it takes very lengthy, very time taking, and the mathematics becomes complicated in those cases. But using work energy theorem, we get those things very easily, right? As we are having the equation of motion in our higher class, in our higher grades, in our grade school, graduation school, we study another type of that equation of motion only, we can say. Okay, they are called Lagrangian equation of motion or Lagrangian mechanics. There is a different I think chapter or something like that, where again we relate those things with energy, and it plays a crucial role in for if you want to learn engineering or something like that. Now we use work energy theorem. Okay, so I am writing WET, which means work energy theorem. So applying work energy theorem, work done by all force is equal to change in kinetic energy, that is kinetic energy final minus kinetic energy initial. So here the work done by mg is 0 because there is no displacement in the vertical direction. Work done by normal is 0. If I say that the surface is smooth, so work done by friction also becomes 0. So there is only one force that is acting in this system, that is this. So the work done by this force will be equal to force which is 20 into displacement, that is 4, okay, which is equal to final kinetic energy. Now kinetic energy is equal to half mv square, okay. So this v is the final velocity which we want to find. We know the mass, we'll put it minus initial kinetic energy as this is in rest. So mv square, half mv square, v is 0, so this will be equal to 0. Now 20 into 4 gives us 80, mass is equal to 2, so 2 and this half gets cancelled into v square, or v square is equal to 80, so we can say that v is equal to under root of 80. How many of you clear? So this is how we use the work energy theorem, and you can see that both of them are giving the same answer, that is velocity is equal to under root of 80. In both cases we are getting the same velocity, okay. So I hope now this acts as a verification that this is also correct, or the explanation which I am giving, the work energy theorem, is correct, and we can use it in place of our equation of motion. So in this chapter we are going to use the work energy theorem. Now let us do 2-3 questions before moving further. So now if suppose I take a question, suppose force I have given, force is equal to 2i cap plus 3j cap plus 5k cap. Displacement is 4i cap plus 5j cap plus k cap. Okay, now we are told to find the work done by this force. Okay, so work done by this force is equal to the dot product of force vector and the displacement vector. So work done by force is equal to the dot product. So I am simply taking the dot product, that is 8 plus 15 plus 5 joule. So work done by force is equal to 28 joules, right? Now a basic thing is that the SI unit for work done is joule, okay, which is represented by J, or if we see in this way, that work done is equal to force into displacement. So SI unit of force is Newton and displacement SI unit is meter. So it can be also equal to Newton meter, or in some places it is like this. Okay. So both of these are the SI unit for work. Okay. We use them as the SI unit. This is the most basic thing which I am telling. And while we are solving the question, we should not forget, we should write it. Okay. Write this joule. So this was a basic question. Now let us increase the level of question. A block is there. The mass of the block is 10 kg. Okay, mass of the block is 10 kg. Acceleration is 2 meter per second square. Okay, acceleration is 2. So now what we need to do, we need to find the work done by different forces which is acting in this case. Okay, let me also include friction force. Okay, friction. Now coefficient of friction is 0.6, right? Acceleration is acting in this direction. So now we are going to find work done by different work done by different forces. So first let us start with work done by mg. So if we make the FBD here, this is the mass and mg is acting downward. Okay, mg is acting in this direction. In this way mg is acting, right? In this direction mg is acting. Now we see that the displacement of this block is here in the x direction, in the x-axis direction. So displacement, the object is moving like this. The displacement is in the x-axis direction. It is not in the y-axis direction, or it is not in the vertical direction. Okay, it is not in the vertical direction. So I can say that it is equilibrium in the vertical direction. So though there is a force acting, but still the displacement in this case is 0. But we know that force is equal, work done is equal to force into displacement. So force is mg, but displacement is 0. So work done is 0, right? Same, if we are told to find the work done by normal, then what we see is that normal is again acting upward to the body. Okay, it is acting like this. So there is a force, but displacement in this case is again 0, right? Because it is equilibrium in the y direction. So F into 0, that is again 0. So work done by normal force is also equal to 0. Now I want to find the work done by this applied force. So work done by this F is, now mass into acceleration. Mass is 10 kg and acceleration is 2. So by the product of mass into acceleration we get the force. So force is 20 Newton and the displacement is 20 meter. The displacement is 20 meter. So our force should be mass into acceleration and into displacement, that is 20. So the work done is 400 joules, right? Work done by this force. Now again, I know that you are focusing on this friction force. You are telling that there is a friction force acting behind this object. So how can we forget it? No, I am not forgetting. Remember the starting of our lecture I told that there are many forces which are acting. So, and there are different displacements for different forces, right? But we can find the work done for one force and one displacement at a time. So whenever we want to find the work done of a particular force, we will focus on that force and the displacement caused by that force only. So in this case the force which is applied is 20 and the displacement is 20 meters. So the work done by the force F is 400 joule. Now work done by friction. So now see, friction is acting in the back direction. So first friction force is equal to mu into mg. Okay, mu into mg. So our mass of the block is 10 and acceleration due to gravity is also 10. So mu is 0.6. So the friction force becomes 60 minus 60 because it is acting in the back direction. We are considering the sign convention that in this direction, whenever the particle moves in this direction or as the acceleration is in this direction, so this direction must be the positive direction, and whenever the object is moving in backward direction, it is negative. So this is the frictional force, and the displacement is again 20. Okay, displacement is 20. So work done is minus 1200 joule. Okay, minus 1200 joule. Okay, wait. Let the coefficient of friction be 0.1. Okay, now it is going to be perfect. So if it is 0.1, if the coefficient of friction is 0.1, then the force which is going to be applied will be, I'm sorry for this interrupt. So, I'm sorry, the coefficient of friction is 0.01. Okay, the coefficient of friction is generally very less, so let us consider that it is 0.01. So zero 0.01. Now the frictional force which is acting in the backward direction is minus mu into mg. So 0.01 by 0.01 into 100. So it is going to be 1. I hope it is clear. And the displacement is 20. Okay, displacement is 20 meter. So overall force, the work done by friction is minus 20 joule. Okay, I'm sorry for this interruption. I hope, please consider. Now if we are obviously going to apply the work energy theorem, and we in our subsequent classes we will going to learn this work energy theorem in detail. We are going to practice more and more an advanced level question for that in our subsequent classes. But before that, we need to find the work done by all the forces. So the next question is, find the work done by net force or by all force. Work done by all the forces. So work done by mg, work done by normal, work done by friction, and work done by this applied forces, that is F. So work done by mg is 0 plus normal is 0 plus work done by friction is minus 20 joule, and work done by this applied force is 400 joule. So overall work done by all the forces becomes 380 joule. I hope this is clear to all of you. I hope this question is very easy and it is clear to all of us. Right everyone? Now let me tell you one thing, that in the Newton laws of motion chapter we have learned about lifts, right? Where we observed that the displacement was different when we observed from ground frame, and also when we observed from the lift frame, the displacement of the block in the cases were different, right? For example, if a lift is taken, okay, this is a mass M kept and this is suppose a person which is standing. The lift is having an acceleration above. So if one more person sees the lift from the ground, it will see that the lift is moving a displacement. Okay, the lift has moved, the object, this mass has moved a displacement h. Okay, this will be seen by this. But whenever, let me visualize this thing. Let's visualize. Suppose this is the object and we the people are watching it from the ground reference. So when this object moves above, we see that the object covered a displacement. This is the displacement the object covered. So whenever the object is moving like this, so it is covering a displacement h, right? So this is the displacement. This is the displacement in this case. But suppose if this is a person, suppose I am sitting in the lift and I am observing it. So what do I will observe? I will observe that this object is also in rest. This object is in rest. Okay, I will observe, and if it is in rest, then what will the displacement in this case? It will be equal to 0. So displacement from ground is not equal to 0. Why? Displacement from lift is equal to 0. So the displacement is different. Therefore, we know that work done is equal to force into displacement. Now displacement is different, right? Let's consider that the force is same, but as the displacement is different, so the work done is also going to be different. Therefore, if you observe a displacement from different frame of reference, then the work done will be also different for different frame of references. Therefore, we knew that displacement is dependent on frame of reference. Similarly, work done must be also dependent on different frame of reference. It is dependent, okay? It is dependent on different frame of reference. So this we need to make it clear. Now let us go to a different question. Let me now focus on a different question. Let's take the previous question only. This is 10 kg block. The coefficient of friction is 0.01. Okay, the coefficient of friction is point, and the coefficient of friction is 0.01. Now the only difference which I am going to make is that now the force is acting in a direction, in an angle. If now this is my angle, let us make this angle, let us say that this angle is 30 degree, okay, or I can, for my easy in calculation, let's say it is 60, and the force is 10 Newton which is acting in this direction. The force is acting 10 Newton and the displacement is 20 meters again. There is friction is not equal to 0, friction is equal to 0.01, the displacement is 20 meter and the force is acting on an angle which is 10 Newton. So now we are told to find the work done by different forces. So first of all, I want to find, suppose, the work done by mg. So similarly, when we are going to make the free body diagram, we'll observe that work done by mg is equal to 0 because it is not moving in the vertical direction and it is in equilibrium. Okay. Now secondly, we are going to find the work done by normal. This is again going to be 0, so we shall have no doubt in it, okay, because it is going to be 0, right? Now to find the work done by frictional force, okay, so friction is acting in backward direction. What is the mg? Okay, mg is our, we need to find the mg. Mg is our, what is mg? Mg is this 10 into 10, 100, and 100 into this again becomes 1 but with a minus, and the force of this component, because it is angle acting in a direction, so let's make the component. So F cos theta is 5 Newton into 5, okay, so work done by friction is minus 5 joule. Okay, I hope you have got this answer only, but this answer is wrong. Okay, why it is wrong? Now why this is wrong? You may think that this is our mu into mg, that is, this is our frictional force, this is our this is our I'm sorry, this is our frictional force, and this 20 meter is our displacement, so the force should be minus 20 joule. But why it is not minus 20 joule? You might be thinking this, that it must be equal to 20 joule. Then why it is not equal to 20 joule? The reason of this, my friend, is that in this case there is a twist, that the block is, and the force is acting on this block at an angle. So when it is having a component in this direction, it must be having a component in another direction also, in the perpendicular direction. So that is, if sine 60, which is equal to 10 root 3 by 2, or we can say that it is equal to 5 root 3. So this component is equal to 5 root 3 Newton, right? Am I clear? So work done is equal to frictional force is equal to mu into mg. But if we make the FBD, we haven't made the FBD properly. So mg is acting downwards. This root 5 root 3 Newton is acting in the upward direction, and one more force, that is normal, is acting. So as this is in equilibrium, mg must be equal to the normal force plus, it should be equal to 5√3. okay, it is should be equal to this. So what should be the value for our what should be the value of this? So it should be equal to mu mg, then we will apply the displacement. So we are going to put this and then we'll find the displacement, which is multiplying into 20, and we'll get our answer, right? So by this we can solve. And please remember this mistake which I've made right now, because we learn from our mistakes, and the questions which we practice give us more clarity. So it is advised to practice more and more number of questions, because the more number of questions we practice, the more we get better into this. So work done by the applied force is equal to now 5 into 20, which is equal to 100 joule, right? This force I am talking about, the component, this component of force, which is equal to this, right? Am I clear to all of you? So this is our third question. Now let me now generalize, okay, different cases. Whenever, now every time we are not going to apply this cos theta and all, so I am now going to generalize a few cases. Let me define those cases. So if let's suppose that this is the mass, okay, and the force is this direction, and we are having a displacement in this direction too. This is the mass. So in this case, work done is equal to FD cos theta. We know that by definition it is FD cos theta. So magnitude of force into magnitude of displacement into the cos theta. So the angle between force and displacement is equal to 0. So what we'll say, that theta is equal to 0 in this case. Theta is equal to 0. So in this case what we'll say, that cos 0 degree. So work done will be equal to force into displacement. Since cos 0 degree is equal to 1, this we know, right? So FD into 1, which gives us force into displacement. Now this is when they are parallel. Now let us suppose that both of them are in opposite direction. That is, displacement is in this direction, or better to say that force is in this direction and the displacement is in this direction. Okay, in both are anti-parallel to each other, both are opposite, like we observed, like we seen in the friction case, that friction is acting opposite and displacement is going that side. So here what we can say, that the theta is our 180 degree, right? Theta is equal to 180 degree. Okay, so work done is equal to FD cos 180 degree. Now work done is then equal to force into displacement. Value of cos 180 is minus 1. So work done is equal to minus force into displacement. So I hope it is now clear that why, when friction force is applied in this direction and the displacement is in the forward direction, or when they both force and displacement are in anti-parallel direction, why a minus sign is applied. So from both the ways we can understand. Okay, we can understand from both the ways. So this should be our approach of learning. This should be how we learn. Okay, we should learn like this. Now the case which I have told you in the previously, which I told you, that suppose mass m is kept here and force is acting an angle suppose force is acting in this direction, okay, and the angle made is theta. So, and the displacement made by this is this, okay. So work done is equal to force displacement into cos theta. Now this if also we can understand by the definition, work done is equal to force into displacement. Thus force component will be, this component will be F cos theta. So F cos theta into displacement. So the value of cos theta will put and force into displacement. So and cos theta is going to be work done in this case. This case work done is this. Okay. So now let us now generalize or write all the case which we have studied till now. The cases are when theta is equal to 0, then work done is equal to force into displacement. This is the first case. Now when theta is greater than 0 but it is lesser than, suppose 180 degree if we say, then the or if we say it is lesser than 90 degree, then the work done is force displacement into the cos theta. So this we need to remember. Now the third case which arises, that when the what we can say, that when suppose a force in upward direction or force in downward direction is acting, the displacement is like this. So what should be the force, what should be the work done with respect to this force? So work done is equal to Fd into cos 90 degree, because the angle between force and displacement, or angle which is making by force and displacement, is 90. So cos 90 is 0. So force into displacement into 0 is equal to 0. Can you now understand that why in those cases the mg, work done by mg forces, was coming 0, right? I hope you can understand. So from both the reason, this is the, from mathematical definition you can also understand, or you can understand that the mass is at rest in the vertical direction. In the vertical direction the block is in rest. So in vertical direction it is in equilibrium, and whenever it is in equilibrium there is no displacement, it is at rest. So how there can be displacement in this vertical direction, right? So as displacement is 0, force into displacement, so which makes the work done is equal to 0. Similarly, if the force is acting in downward direction, the same goes for this case also. So what I will write, that whenever the theta is equal to 90 degree, then our work done is equal to 0. Okay, our work done is equal to 0. And now our last case, that is when theta is 180 degree, then work done is equal to minus F into D, that is force into displacement. So these are some of the important points which we need to keep in our mind, right? So this we need to remember, which will be useful in our questions which we are going to answer. So these things we are going to apply in our questions. Okay, these are the things, these are the points which we are going to apply in our question sessions. Now I am going to move on our next question. Okay, we are going to now move on our next question. So now let us see that what is going to be that question, right? So now we have studied that we have studied that mass, that block we have learned. Now let us do something different, right? Let us study something different. So say that I am taking a pulley, and suppose two blocks are attached on two different sides of the pulley. Okay, now this is not an ideal pulley, as you can understand. Okay, because the friction in these strings are zero. Obviously we are going to study ideal pulley in the rotation chapter. Okay, so suppose this block is 2 kg, this is 3 kg, and now it is kept, this is initial position. I am holding both these objects. Now I have released, when I have released, when I have dropped. Okay, so after releasing it, what it becomes is this, that this 2 kg block goes 10 meter above from its initial position, and the 3 kg block goes 10 meter below its initial position. So this was their initial position, and this 3 kg block of mass is going downward, and this 2 kg went above. So we can say that acceleration on this block is acting downward, and acceleration here is acting upward. In one line we can find the acceleration, which is equal to net force, which is change in net force divided by the total mass. So mg is, in this place, will be acting 30 Newton. In this case it is going to act 20 Newton. So 30 minus 20, 10 Newton divided by the total mass, that is 3 plus 2, 5. Okay, so acceleration is equal to 2 meter per second square in this case. Now if I want to find the tension force, in this case, so what we can say, that tension is applied in this way. Okay, so I can say that this mg minus tension is equal to our net force. So the net force is going to be, let me say it is 10, right? 30 minus, so this is going to be 10, and in this case again we will find that mg minus t is going to be 10. right? But the mass is different for each cases. So this is going to be equation 1, this is going to be equation 2. Now solving this equation, what we get, that let me put the value 30 30 minus t is equal to our 10. So when we will solve this equation, okay, or if we apply a formula, there is a formula, I hope you all guys know that formula. So when we will apply the formula, or when we will solve this two equation, we can easily see that the tension here is 24 Newton. Can you see that? The tension in this case, when we write the equation and we solve it, we get the tension equal to 24 Newton, right? I hope it is clear to all of you. Now try to see that if I want to find the work done by gravity on the 2 kg block, okay, on 2 kg. So what will be the work done by gravity? So now again mg is acting downward, so mg is acting 20 and displacement is going above, so there will be a minus sign, because we learned that when the direction is anti-parallel, then work done is minus F into D. So minus 200 joule is the work done in this case. If I say that work done of G by 3 kg, so work done will be, as the displacement is it is going downward and the mg is also going downward. So when they are parallel, Fd cos 0 degree, that is equal to Fd into 1. So it will be equal to 30 into our displacement 10. So it is going to equal to 300 joule, right? Now similarly we can find the work done by tension. Okay, we can find the work done by tension force. So WD, work done by tension on this 2 kg. So now see, tension is going upward, and the displacement is also going upward. The block was initially here and the displacement is upward. The block has moved, the block is displaced 10 meter above its initial position. It is shifted 10 meters above its initial position, and the tension on the block is T, which we can see that it is above. So tension is 24 Newton and this displacement is 10 meter above. So when both of them are parallel, work done is force into displacement into cos 0 degree. So work done by tension on this 2 kg block is equal to 240 joule, that is 24 into 10, and cos 0 degree is 1. Okay, now work done by tension on 3 kg block. So work done by tension in this case becomes, now you can see that this was its initial position and final position is here. So the block is shifted 10 meter, or it is displaced 10 meter downwards from its initial position. Therefore we can say that tension, the force and the displacement are anti-parallel to each other. So the work done is Fd cos 90 degree. Cos 90 degree value is minus 1. So work done is minus of Fd, minus of force into displacement. So minus 24 into 10. So which is equal to minus 240 joule. Now remember or recall the previous lectures in the Newton's law of motion, where your teacher must have taught that the work done, the overall work done by the tension force is equal to 0. The overall work done by the tension force is equal to 0. Can we simply say net work done by tension, see, plus 24 joule and minus 24, both of them gets cancelled and net work done by tension is 0. So these all are the questions which we have practiced in our this lecture. So please remember the points, please revise, recall, and come to our next class, which we are going to take in our next Saturday. I am sure that I am going to take on next Sunday, and the video will be Saturday, and the video will be uploaded on the next Sunday. So please practice this question, as this chapter is new. This chapter is very interesting and it is going to be very fun studying with me. Okay, so this was a basic introduction of this chapter. This was the basic things. We have learned how to find the work done by force, basic forces, some tension we found, normal, mg we found. So constant force work done we have learned. So now we have to learn spring force, how to find spring force work done, and few pseudo force and all. Then we are going to, okay, then we will move on our next lectures and we are going to continue with this chapter. So I hope this is clear. And also in the comment section, people kept encouraging me, and you all are guys very helpful. You are guys supporting me. I am feeling good. Please keep supporting me like this. And there were few issues like regarding the brightness. People said that the brightness was not proper, the text was not visible. So I hope that today this issue will not come, and I will take care of this issue. Okay, and please, if any issue you face in the concepts in learning, you can ask in the comment section. I will surely clarify your doubts, and please give the feedback so that I can understand what should be done to make this lectures better for your understanding, what should be done for the betterment of our classes. So that's all from our side. Thank you. Jai Hind, Jai Bharat, and let's meet in the next lecture. So thank you.